All right, everyone, so it's time to begin, and I just want to let you know that homework 3, which is due next Monday, is now posted, and it covers what we do today. So by the end of today, you'll be able to do this, and all these pre-lectures for what we're going to be doing today are also posted. So we're going to try to cover. We'll certainly cover chapters 3 and 4. We might cover chapter 5 as well. We might get a little ahead, which would be great. Okay, so, and as you know, you have homework 2 due Wednesday, and that covers last week's stuff. All right, so let's go to the document camera and start where we left off. What we were talking about here, if you recall, is we're doing descriptive statistics. So we have all the numbers, the whole population of numbers in front of us, and we're just looking at first summaries of measures of first center. So a numerical summary of the center of the list of numbers, or the center of the distribution of numbers. Okay, and we gave a really, really simple example here and looked at these properties, how we looked at the mean and the median. The mode is not used very much, so we're not going to really talk about it much. It's just the single most repeated number on the list, but we're not going to really deal with that much. Okay, so so we saw how the mean and the median change when you add the same number to every number on a list. Here's a simple example. Then, of course, the mean and the median just goes up by that number. That number gets added or subtracted to it if you add a positive or negative number. All right, same with when you multiply, the same thing. If you multiply every number on the list, well, that increases every number, like multiply by 2. That would multiply every number by 2, so it would multiply the mean and the median by 2. And then we said, but here's where you'll see a difference between the mean and the median. The median is not sensitive to extreme values because it's the middle number. So if we, for example, add 20 to this largest number to make it 23 here, well, the middle number is still 2. So the median is not, it could be 23 million, and the median would still be 2. It's not affected by the extreme values. Whereas the mean takes into account every single number on the list. And so if you add 20 and there's 3 numbers, it's the same as you're adding those 20 and dividing it by 3. So you're adding, because there's 3 numbers here. If there were 10 numbers, and you added 20, you'd be adding basically 20 divided by 10, 2 to each number. So that really increases. That affects the mean. All right. So any questions on that? That's what we did last time. And that's pretty simple. And now we're going to look at numerical summaries of the measures of the spread of a distribution. Okay, so how far out the numbers are, how spread out they are. And the simplest one is the range, which the range is defined as the difference between the lowest and highest values, okay? So it's just the maximum number minus the minimum number. So that's very easy. It's just your max minus your min. And in this case, the maximum is what, 2? And the minimum is -5. So it's just 7. That's the simplest one. It just takes into account just the highest and the lowest numbers. Now the standard deviation is much more widely used, of course, because it takes into account not just the smallest and the biggest numbers, but every single number on the list and how far they are, their distance from the average number. So it measures the typical range of the deviations from the average. So it's basically like an average of the distances from the average. It's a little bit different than that. We'll calculate it in a moment. And the variance is just the variance is just the standard deviation squared. All right. So let's look at the calculation for the standard deviation, which is right here. But first, which of these distributions is more spread out around the average? Which one would have a larger standard deviation, and why? Well, do you see how the numbers here are all bunched up? The average is right in the middle here is 0, and the numbers are all bunched up around the average here, right? And here they're more spread out around the average. So this distribution would have a larger standard deviation because it's more spread out. This is more bunched around the average. The average and the mean are the same thing. I'll use them interchangeably. They just mean exactly the same thing. All right. Now, so what is the calculation here for computing the standard deviation and the variance? Well, it's first you have to find the average of the list, and then you have to find the deviations from the average, which is just the distance from the average, positive if they're above average, negative if they're below. And then, here, why don't we do it with this list of numbers, okay? And we can walk, here it is in symbols. And actually in symbols, I should have probably, we're not sampling here. Pretend this was the entire population, these numbers. The numbers we have is the entire set of numbers we're interested in. We're not using them to infer some larger population. Well, then I really should have been using here mu, right? The Greek letter instead of x bar. It doesn't matter so much here, but we should write, we should really change, if we have the whole population, you should change this x bar here to mu. I just noticed that. Okay, for population standard, for if you're computing the population. If we have the whole population, which we do. But I don't want to get it all messed up, and it doesn't make any difference here. It makes it, when does it make a difference? It makes a difference if you want to distinguish between your sample and your population. Like you're taking a sample from a big population and want to use that sample statistics to estimate the population parameters, like we will be doing in inferential statistics. So this is fine for these directions. All right, so now let's do this, okay? So the first thing we're going to do is find the average or the mean, and so we'll just add these all up and divide by 7, because there's 7 numbers, and you can probably just see it's going to be the middle number here, because it's symmetrical. All right, so that's what we did there. Now, what's the next thing we want to do? We want to find these deviations from the average, right? Well, what do we want to do then? The deviations from the average, what we just want to subtract the average from each one of these numbers. So if you subtract the average from 3, it doesn't deviate at all. It's 0. These are below, so we'll say that. So these deviations right here, what are they? These deviations are, here, I'll write them down here. The deviations, and it's just the number, these are the number minus the average, just your value minus the average. Okay, so it's 0, so it's -3, 0 minus 3, -2, -1, 3 minus 3 is 0, and 1, 2, and 3. There's 7 of them. Okay? And just remember that if they're above, 4 is above the average, so it has a positive deviation of 1. 2 is below the average by 1, so it has a negative. So the negative sign just means it's a below average deviation. All right, now you might think, well, why don't we want the average, we want the typical deviation, so why don't we just take the average of these, add them all up, and divide by 7. But you can see if you add them all up, you'll get 0. And they're clearly, we want a measure of the distance, not neglecting sign. So the deviations always sum to 0. So we have to do something else. So we should write that down. The deviations always sum to 0. That's important. Okay? They always sum to 0. So the most straightforward thing to do would just be to take the absolute value of these numbers and then take their average. And that's done for certain, if you're using generally, for certain types of statistics, we do that, especially when we're using, but it doesn't, if we did that, it's just not as mathematically useful a way to measure the sum, because for one thing, the graph of the absolute value comes to a point at the end, so you can't take the derivative at 0 there, so it doesn't work well at all. So what we do with it's just not useful. So what we tend to do instead, another way to get rid of these signs is by squaring. So we're going to square each deviation, okay? So that's what we're going to do here. If you square the deviations, you get rid of the sign. So you get 9, 4, 1, 0, 1, 4, and 9. All right? So now if you take the average of these, that's the average of the squared deviations. That's what's called the variance. Okay? So that's step 4, the variance. So the variance is equal to, you just add all those up, just take the average of those. So it would be 9 plus 4 plus 1, right? That's 14 plus 0 plus another 1 plus 4 plus 9. So that's another 14, 28 over 7. So that would be 4. Okay. And that is, that's a very, very common measure of the spread. It's used all the time. The problem is it's in squared units. So if these were, I don't know, something like how many, this doesn't come out in the same units as that. So if you're talking about variance would be like if I said, I don't know, let's say the average of your exams are 70, and you want to know plus or minus about how much. 70 scares you. They're more like probably 85. So 85 plus or minus about how much you wonder. Not everybody gets an 85, so you're wondering what the typical spread around 85 is. That's very informative to you. So it's probably about 10. But then if I squared that, that would be 100. And that doesn't really make sense. The exam scores are about 85 plus the squared unit. So it doesn't really make sense in terms of an intuitive description, but it makes sense a lot in terms of a lot of the calculations we're going to be doing. So we're going to be using the variance a lot. But then now we want to square root the variance, we want to get the standard deviation, so we get it back in the same units as the original numbers, and so we take the square root of the variance, which in this case would be the square root of 4, which is 2. So you see, you could say, okay, these numbers, the average of these numbers is 3, and the typical deviation from them is what? From that is about 2. This one deviates by 1, this one deviates by 2, this one deviates by 3 on both sides. So that makes a lot of sense. All right, any questions on that? Yeah?
Could you explain the difference between the variance and the standard deviation? Because aren't you saying that they're like the measure from each point, data point, whatever, from the mean? How are they different?
What this variance is the deviations, the distance from each point, like each one of these, but then you square them. And then you take the average of the squares. And that comes up a lot in statistics, the sum of squares, instead of, because they have a lot of nice properties. The variance of the sum is the sum of the variance. We can add them really easily as long as you have independence between two quantities, two lists. You'll see sum of squares all the time. In fact, a really good way to think about this, another word for standard deviation, is the root mean square. Why is that? The root mean square of the deviations. You can think of it, here's the square root, the root. There's the mean. We're taking the square root of the mean of the squared of the squares and of the deviations. Root mean square of the deviations. So another word for standard deviation is root mean square of the deviations. And another word for variance is the mean square of the deviations. Okay? And another word for this, well, we can just, too many words, okay? And you don't really have to, if we look to our summary, I think I say that back here. Let's see. So you have another place to find that, because it's used a lot. So I say that standard deviation, this is on page 18, the standard deviation measures the typical spread of the deviations from the average. It's usually just a little bigger than the average of the deviations neglecting sign. If you took the absolute value of it, it's just a little bit bigger. And it's calculated by taking the root mean square of the deviations. Okay? And the variance is the standard deviation squared. But it's a step on the way to finding the standard deviation. So it's easier if it's a step on the way. Okay, and it's never negative. Why could it never be negative? Because it's a distance, right? What would be having a negative standard deviation mean with this list of numbers here? What would a negative spread even mean? That doesn't really make sense, a negative spread, right? Around so the standard deviation is never negative. What would a zero standard deviation mean? That's the lowest you can get. If you had zero standard deviation, then every single number would be at the average. So they'd all be the same, right? That's the lowest the standard deviation can go. So wouldn't that make sense? If all the numbers were the same, you'd have no spread at all. All right. So now we had the properties of the average and the median before. We said if you add or subtract the same number to the average or median, it will, to every number on a list, it will go up or down by that number. But what will happen with the standard deviation? If you add or subtract the same constant to every number on a list, okay, let's try it. So let's just try it with our list here. This list of 0, 1, 2, 3, 4, 5, and 6. What if we added 5 to every number on the list? If we added 5 to every number on the list, what would we get? So we'll add, same way we did 5 to every number on this list. And when we do, what do we get? We'll get 5, 6, 7, 8, 9, 10, and 11, right? The 9 numbers. Now, did it change the spread? The average went up from 3 plus 5 to 8, but it's still spread out by the same amount. This just shifted over, right? You can see, do the deviations change? You get a new average here. You'll get a new average equal to what? 3 plus 5 equals 8. That's our new average. But the deviations are going to be the same. Deviations will be what? If you subtracted 8 from each number on this list, you'd get the same deviations, right? So you'd get the same deviations. So obviously you'll have the same SD and same variance. Does that make sense to everyone? Okay, so you just shifted it. You didn't change the shape. I don't have room to put that on the notes, but you can write it somewhere. And the point is, I'll write it here, that it just, the numbers shift. If you add a positive, they shift up. If you add a negative, it shifts down. So we'll just write that the numbers shift up or down, but the spread stays the same. Up or down if you add or subtract, but the spread, which is what the SD and variance is, spread stays the same. Okay, what about if you multiply or divide every number on the list by the same constant? What would happen? It says the SD would be multiplied or divided by the absolute value of that constant. So let's try that. So this was property 1. Now we're doing 2. So let's say we multiply. Let's multiply every number on this list. Every number by what? 2? So what's going to happen? So 0. See how it's going to get spread out? 0 will stay at 0. 1, 2, 4, 6, 8, 10, and 12. And on a number line, it would get spread out. See? Now our range is twice as big. All right? And then what do we have? Our new average is equal to the old average times 2, which is 6. And so what happens to our deviations? So what are our new deviations? Our new deviations would be what? Can you see what would happen to them? They would just, what would we get? Instead of these deviations, we subtract 0 minus 6 is negative 6, negative 4, negative 2, 0, and then 2, 4, and 6. They get multiplied by 2, right? So the deviations double. And if we multiply by 3, they triple, right? Double. So, of course, the standard deviation doubles. But what would happen to the, and the variance would be what? The variance would get multiplied by what? Would be would quadruple, would be times 2 squared, because the deviations are squared for the variance. So if the deviations are doubled or they're tripled, let's say they're tripled, and then you square them, that would be like multiplying by 9. So the deviations, let's write that down right here. So if you multiply or divide every number on the list, the standard deviation would be multiplied or divided by the absolute value of that constant. Why the absolute value? Because it can never be negative. And if you multiply or divide every number on the list by the same constant, we did 2, and then the variance got 2 squared. If we did 3, it would be 3 squared times 3 squared. It's multiplied or divided by that constant squared. So if we multiplied every one by 6, the variance, the standard deviation would get multiplied by 6, but the variance would be multiplied by 6 squared. Any questions on that? Does that make sense to everybody? Does it? All right. So let's see. So this, why don't we just say the spread changes. It increases or decreases. If we divided every number, if we multiplied by a number less than 1, it would decrease. The spread would decrease. So the spread changes. Right? And the variance changes by the same number, and the variance changes by the square of that number that you multiply everything by. Now, here, as we said here, so this absolute value comes in because these can never be negative. And okay, so here's a feature I talked about before that we're going to be using a lot, and that's because what I say is the variance of the sum is the sum of the variances, and that's as long as A and B are independent. And we'll talk about this more, but basically this is a property of them being squared, whereas this wouldn't be true. This wouldn't be true of the standard deviation because of that square root sign there. The square root sign, they wouldn't. Square root of A, you couldn't say the square root of A plus B is the square root of A plus the square root of B, even if they are independent, even if A and B are independent. But we'll talk about this more and show why that's true. But this is why the variance is used in so many calculations, because it's easy to manipulate. All right, I think that's pretty much that. And so now, let's look here. And let's make sure all these properties I just talked about are just summarized here. So if you're ever unsure about anything, always read the summaries. Like we talk about how extreme values have a strong effect on the average. The average, we talked about that last time, moves towards the extreme values. Remember I said if we took everybody's average income here, or average parents' family income here, and took the average of it, probably something like, I don't know, maybe 60, 70,000, something 70. But what if somebody like some billionaire walks in, like Bill Gates walks in or something like that, and now he's a student in the class, or his kids or something, well then it's just going to skyrocket, right? So when you, for something like, because it would be as if his income was evenly, you take the additional income and all his income, it would be evenly divided among all of us. It would raise the average way up. Does that make sense? So you have to think about what, this is one way that statistics can be very misleading. Like I remember Trump was saying that the average tax cut, if he was elected, would be something like $9,000 or $10,000. But that's because he was going to give these huge tax cut to the rich. And since they'd get huge tax cuts, the average would skyrocket up. Whereas most people interpreted that to mean, oh, I'm an average guy, my taxes are going to go down by that much. So you have to be very careful about which one you're, the difference between that when you have skewed data, very skewed data. The average is very sensitive to the extreme values. So if the histogram has a long right-hand tail, the average is, okay, so we haven't talked about histograms yet, so I'll have to do that. But basically, if there's extremely big values, then the average is going to go way up. Extremely small values compared to the other numbers, it will go down. Whereas the median doesn't. So that's often why the median is used. The median is used in skewed data. All right, and what else? So here's, we talked about this, what the standard deviation measures and how it's not negative. And this is super important. This is a great way to check your calculations. If you're going to have to calculate on your homework and on the exam a standard deviation for a simple list of numbers. So this is a great check along the way. If your deviations do not sum to 0, you've done something wrong. They don't have to be symmetrical like the way that but they have to sum to 0. The positives and the negatives will average out. And then we talked about how what happens to the average and to the median under certain conditions. All right. Okay, let's go on now. And now we're going to talk about measures of, we're going to talk about graphical summaries of the data. So we talked about numerical summaries of the data. The main ones that we're going to be using are the mean, and the median, and the standard deviation and the variance. But we're also going to be looking at graphical summaries of the data. And you're probably familiar with bar plots. Wait a minute, I'm not even going to talk about that because you probably all know bar plots. I was going to do histograms and box plots, but we don't really have time, so I think I'm just going to, I want to get through this whole notebook if possible. And box plots are pretty easy to understand, and I can give you the notes for them if you want, but we're not going to go over them, or you're not going to be tested on it. So for this class, we're just going to look at histograms. All right, So now, what are histograms? It looks like, here's a histogram. It looks like a bar graph. The difference between a histogram and a bar graph is that this x-axis here, this is drawn to scale. So histograms are used for quantitative data, like here's final exam scores of a group of students, and notice that this 0 to 50 block is 5 times as wide as the 50, as this is 5 times as wide as the 50 to 60, because it's in a bar graph you'd put 0, even if it was numerical data, you don't, the widths don't necessarily are drawn to scale. They're just all the same. So that's the big difference. All right? And then the other big difference is that in a histogram, we look at areas to represent percentages, and the total area of all the blocks is always 100%. So they're also, when you do a smoothed out continuous, when you're looking at continuous data, right now we have discrete data, but when you're looking at continuous data, these histograms are known as probability density functions. And in both, when you're looking at discrete and continuous data, like if we did a smoothed out version of this, it would be more a continuous. I mean, this could actually be our data, but this is, I just was looking ahead for some of you. I was looking at your survey data, and I saw some of you were in taking upper level stats classes, so I want to relate to what you learn in Stat 400 and 410. All right, so this axis is density here, right here. Let's write that down. And what is density? It measures, in this case, I have it written as percent for each point here. All right, so it's how crowded each point is. And the area, so that's why I say the vertical axis measures the density, the crowdedness of each interval. So for example, this is half, this is 0.5 here. So this is 0.5% per point. And this one is the most crowded, this is 2.5% per point. I'll just put the heights. I can put the heights over all of them so you can see it easier. This is, because it's hard to read this. So this has a height of 1, this has a height of 1, this has a height of 2, and this has a height of 1. All right, so now this is a really important point right here, that the histograms use areas to depict the percentages. The width of each block indicates the size of its category, and its area indicates what percentage of the data belongs to that category. All right? So, and unlike bar graphs, the x-axis is always drawn to scale. So if we wanted to find the areas of all these, what would we do? Well, the area of a rectangle is obviously what? Its height times its width. You know, so the area of this would just be what? It would be, so the area of this block, so the area of this block would be the height of the block, which is 0.5. Let's put the units in so you can see how it works out. Percent over point, and then times the width. So that's the height, and the width is what? 50 minus 0, it's 50 points. So it's times 50 points. So you can see how the points cancel out, and this is just going to be what? 0.5 times 50, 25%. All right? And you can do like all of them the same way. So this is what? 10, 1 times 10, 1 times 10, and this is 1 times 10. And that makes sense because look, they're all the same size. This one, if you stood it up, should be 2.5. You could see that it would be, this area is 2.5 times the area of that. Okay? So what's this one? 2 times 10 is 20. And this is 2.5 times 10, 25%. So these two have the same percentage of the data. So if these are students with final exam scores between 0 and 50, and these are students with final exam scores between 70 and 80, 25% of the class had scores it's the same percentage of students. So 25% of the class had between 70 and 80, and 25% were down here. So any questions on that so far? And what should they all add up to? To make sure that you did it right, they should all add up to 100%. So make sure they did. 25, 35, 45, 70. This is a 90 and 100. Okay? Any questions on that? Now the vertical, often you won't see this axis at all because it's redundant. Once you know these percentages and the axis here, this is sort of redundant. Actually, it can be changed without changing, like the vertical scale can be changed without changing the shape of the histogram. For example, we could change this scale percent per point to percent per half point, all right? Then the 0-50 interval would be 100 half points, right? And the 50-60 would be 20 half points, but that would look exactly the same. All right. So unlike most graphs, histograms don't require a vertical axis label, so often you won't see them. It just makes it easier to read. Any questions on that? So if the intervals were all the same size, if these widths were all the same size, then the tallest block would also have the most area. But here they aren't the same. When the intervals are different widths, the tallest one doesn't necessarily have the greatest area. Let's see, let's go on. So let's draw one, and you're going to be drawing one in your homework. So we can just draw one real simply. So we'll just do this quickly. And all right, so what do we have here? The table below gives the GPAs for a high school senior class of 500. So there's 500 students here. They should total up to 500, and they do. Fill in the table below, then draw a histogram representing the data. The class intervals include left endpoint but not right. For example, 2 to 2.5, GPA includes those with a GPA of 2 but not those with 2.5s. All right? So what do we want to do? So we can fill this in. So the area, the percent of students in each, so it's divided these blocks up. So if this is, it's gone from 0, what is this? Let's just use this one. This will be 1, 2, 3, and 4. So that's 0.5, 1.5, 2.5, and 3.5. So it's given us the class intervals already. Boy, this is a big one from 0 to 2. So that's going to be our first one. And what is the area of that? So let's fill in the area. So 50 out of 500 is 10%. And this is 150 out of 500, so that's 30%. This is 50%. And this is 10% again. All right. 150 out of 500, etc. All right, so it should add up to 100%, and it does. And now, the width of the interval. Well, that's going to depend on what axis we want to do. We could do percent per point. We could do percent per tenth of a point. Should we just keep it simple and do percent per... We're doing it in points here. We could do percent per half a point. We could do percent. We could make this whatever we want. But let's just keep it really simple, and just because these, just do it in points here. So this will just be 2 points. This will be a half a point. This could be 1 point, 3.5 minus 2.5. And this is, again, a half a point. But I didn't have to do that. It probably would have made more sense. People would usually do GPAs by like 2.1, 2.2, 2.3. I could have done per tenth of a point, right? And then instead of having a half a point, I'd have 5 tenths points. Let's just do it simple. All right, so now what do we want to do here? Remember that area equals height times width So for our height, we just take our area divided by our width. So that's 10% divided by 2 points. So that's 5% per point. And these are all percent per points. And the next one's what? 30 divided by 0.5. So that's 60. The next one is 50 divided by 1, so that's 50. And the last one is 10 divided by 0.5, so that's 20. So we're going to label this. This is our density, and it's percent per point, percent over point, and we're going to label it up to 60 here. So that's 10, 20, 30, 40, 50. All right, so now we can just draw it. We can just draw the histogram. So the first one goes from 0 to 2, this far, and it goes up 5. There's 5. So from 0 to 2, there we go. And that percentage is 10%. That goes up to 5, and that's 10% in there. All right, and our next one goes from what? From 2 to 2.5, and it goes all the way up to 60. So it's here. And that's 30%. That goes up to 60. And our next one goes up to 50, right? And it goes from, where are we? Right here? 2.5 to 3.5, and it goes up to 50. So right there. And that's 50. And it's 50% here. And the last one just goes up to 20. And that's 10%. And you can see this has 4 blocks, and this has 4 blocks. They're the same percentage of people. All right? So the interval, this interval, 2.5 to 3.5 has the most people. Is it the tallest? No. Does it have the greatest area? Yes, because that's 50%. What percent of the students had exactly a 3.2 GPA? That would be right in here. That's why I was thinking it might have made more sense to do percent per tenth per tenth of a point. Then you'd have 5% instead of 50 here. Let's not worry about this. Can you see that this 3.2? I haven't even gone over this. Let's forget about it here, and let's do it here. It's be much easier to understand. So let's just not do that problem, and this will help you understand what the vertical axis is. All right, so let's add a problem to this. So let's add this problem, and this will help you understand what this density means, this percent per point. And let me write in the problem. So let's say what percent, we'll put it down here, what percent of the students scored exactly, let's say 77 on their finals. Now, can we answer that? Exactly 77. If we assume a completely even distribution through these intervals, then you could say, okay, exactly 77. That would be right here. And you could say that's 1 unit long. This goes from, I'd have to tell you which endpoint was included, but there's 10 of them in here. Whether it's, let's say it was 7, let's say it's 70, so I'd say, let's say it was 71, 72, 73, 74, 75, 76, 77, 78, 79, 80. That's 10 of them. And so each one would be 1 unit. And so this tells you 2.5% for each point in there. So if that was 77, it would be in the area equals what? Width times height. The width of the interval is 1 if it's 77, and the height is 2.5. 2.5% would be your answer. And that, so another way to look at the density is it tells you for each unit, for each single unit in here, what percent of the population falls in that unit. So what's percent of the population? It would be 2.5%. The same as the height of the block. Because the block is in percent for each point in there. So what percent, another question could be what percent scored, I don't know, 23. And what would be the answer? 0.5%. But it's unlikely that there's an even distribution here, that this is completely even through here. It's very, very, very unlikely, right? So, in fact, it's sort of unless we divided it up different, because, yeah. Well, yeah, it could be, but it's so unlikely. But what you have to do, if to answer these questions, when histogram is drawn this way, well, we'll say for these questions, assume an even distribution throughout each interval. Okay. Does that make sense to everybody? So if I said what percent scored 77 or 78, then it would be 2.5 plus 2.5. 2.5 for each of them. Okay? And this one's too confusing. All right, so let's just forget that one. Now, if you add 1 point to everyone's GPA, how would the histogram change? Let's just, again, let's assume you can go past 4. So assume you can go up to 5 GPA. Some places do. All right, so if you added 1 point to what would change? How would the histogram change? Well, it would shift. So the average and the median would go up by 1 point, but the SD and the variance would do what? Would stay what? Would they change? If you just shifted, would the shape of the histogram change? No. So the SD and the variance would stay the same. Okay. Any questions on that? All right, let's move on. And now, what are we going to do? Finding the mean and the median on a histogram. Okay, so the median divides the histogram exactly in half. 50% of the histogram area lies on each side of the median. It divides in half by area. So here, the median's right in the middle. Here it's harder. You'd have to imagine, you want to divide it exactly in half by area. This is what I used to do with my kids, if they were fighting over some pizza or cake or something, when they were little, I'd have one of them divide the area in half, divide it and the other one choose. And they came really good at getting the median just right, because they both wanted the bigger one. So that's the only way to be fair. Piece of advice, if you ever have kids, they're going to be fighting. It's a great way to deal with it. And it gets them thinking about stuff. All right, so it's hard to do, to think about it. After you do it, it's kind of, the person choosing it, and you could tell for sure which one was bigger. All right, so if the histogram is symmetrical, so where's the average? Well, it's very easy to see here that the average and the median would be the same. So if the histogram is symmetrical, then they're the same. Now, remember what we said about extreme values. If there's a long right-hand tail, so most of us would have income in here, and then Bill Gates walks in and he's way out here, that's going to make the average go up. It gets moved towards the extreme values. Most of the data is around here. These are the extreme values. So a long right-hand tail, like this, extreme large values, is going to, the average gets affected by it. So it's going to go up. Whereas the opposite's true. Like our exams generally look like this. Most people do pretty well. But then there's always people who don't show up, people who really just aren't paying any attention or thinking about anything, and they're going to pull it down. So in every exam I've given, the average is less than the median. It pulls it way down, pulls it down. Okay? So, any questions on that? All right. Now, so for example, let's go back to here. If we wanted to find the median here, with these already given to you, it would be pretty easy. We'd say, this is page 19. The median would be what? 25% plus 10 per 35, 45. It's going to be bigger than 70, but if we go all the way up to 80, it's too much. We just want to add 5% more. So for each one, 2.5. So if we go up to 71, that's 2.5 more. That would give us 47.5, and we'd go up to 72, and it would give us our median. Does everybody see that? Now the average would be less than that because it has a tail here, and if you wanted to figure out the exact average, how would you do it? You would have to say, okay, you'd have to take a weighted average. You'd have to say, okay, 25%. So how would you do that? You take the weighted average and you say 25% of the people, and you just assume it's an even distribution here, so you'd say 25% scored half the midpoint here. So 0.25 times 25 here. And then you'd say 0.1 times 55 plus another 0.1 times 65, etc. So you'd have to take a weighted average. Okay? All right. We're not going to be doing that. It's just too, right now. Okay, so now types of variables. All right, so we talked about quantitative variables being that histograms are appropriate for quantitative variables. What's a variable? A variable is just anything that varies. For example, in our survey data, height is a variable because it varies between all you guys. So that would be a quantitative variable. I also asked you questions like gender. That's a categorical variable because it's not numerically measured. It's a category. I could code it as numbers, zeros and ones, but it's a category. So those are the two big types of, so qualitative data is represented by bar graphs. They fall into descriptive categories. Okay? They'll be used, so quantitative, you use bar graphs. Just because it can't be divided into numeric intervals. And the area, if you took the area of the interval, it wouldn't have any meaning. Whereas this are naturally measured numerical. Okay, and there you use a histogram for numerical data. Okay? Now, quantitative data can be further divided up into continuous and discrete. We've been looking at discrete data. What continuous data means between any two values, you can measure. There's an infinite number of values. Basically, it's just totally continuous. You could break it up into smaller and smaller and smaller intervals, and if you and that's where you would find the areas under the curves. Under these, you'd use calculus, and that's what you do. That's what those PDFs are, and you do in 400 and 410 and higher level math classes. We look at continuous distributions. Discrete distributions have gaps in between the numbers. Like if the exam scores were 78, 79, etc. You can't, there's not an infinite number of, we don't measure an infinite number of between two numbers. But discrete variables are also, often measured by integers. Like an example of a discrete variable would be like family size, something like that. That could be if I ask you how many brothers and sisters do you have, that was a discrete one. How many pets do you own, etc. A continuous variable, the way I ask it, I make it pretty, height, distance, stuff like that could theoretically be measured into smaller and smaller intervals. But the way that I ask the questions, I just want you to give it to the nearest inch. Okay, but that's the idea. Now, what about zip code? Is that going to be, that's numerically measured, but do you think it's going to be a qualitative or a categorical or a quantitative? If I ask you your zip code, you give me a number, but does that number have any quantitative meaning? It's just a label. So that would be, a zip code would be a quantitative, along with your favorite color, gender, etc. All right, so that's the idea. Let's move on. And you're going to be happy because we get to skip this. Maybe you won't be happy, but we're going to skip pages 22 through 25. On Boxplots, it's just, we're not going to be using them very much. If you want to see this and learn it, I can send you the notes for it. So just, or post them if you want. So we're skipping that, and it won't be on the exam, of course, or any homework on it. So now let's just read the summary again and make sure that these summaries are really useful. And let's look at this one and see what it says. All right, so the median divides the area into two equal parts, right? All right, this is all important. The height of each block of a histogram is the percentage of the cases in a single unit of that interval. That's typically how it's done. Although it's arbitrary. You can assign any value to that height. It's redundant because you already have the area once you draw the histogram, and you already have the intervals. Okay, so a variable varies from subject to subject. Okay. Okay, this is the part we're skipping. So we're skipping this so you can ignore it in the summary. I want to say that this is a useful graphical display when the data is skewed, because the measure that you use here is the median, is the middle, and then you look at percentiles. And this is used usually for skewed data. It's very handy, where histogram, it's a more drastic summary than a histogram. It basically just shows the middle 50% of the data and outliers. Okay, so now we're going to tie everything we did together. We can do chapter 5 and we can finish descriptive statistics, and then we can go on to probability, which will be the basis for then doing statistical inference. So that's where we do draw a sample from a population and make inferences, and that's much more exciting. So we're going to finish this, and next time we can start probability. Let's try it. So this is really nice to do now because it ties together the histogram, the average, and the SD into the normal approximation, the normal curve. Okay, so this normal curve is a very, very useful curve, very useful distribution, because it comes up all the time, and it comes up often in nature, but it comes up all the time in inferential statistics, because it's the distribution of no matter what your initial population is, when you take the average, take a sample from that and take its average, and do that over and over and over again, this is the distribution of the averages. So of all the different averages. So it comes up, it's how we do confidence intervals and error bars, and so much in statistics is based on this. So now, but it's also, we're doing the normal approximation here, and there are many data sets that look approximately normal. Basically, things like height, weight, IQ, etc., look very much like the normal curve. Okay? So it's extremely useful. And let's look at the properties. So it's bell-shaped like this. That means it's unimodal. There's only one, there's not two bumps in it, just one. It's symmetric about 0. So the average and the median are 0. Its standard deviation is 1. And its horizontal axis is measured in something called standard units, or z-scores. And the area under it is 100%. Now it also, there's a handy rule here, this 1, 2, 3 rule that you're going to be using all the time, that says that about 68% of the data is within one standard deviation, like this, of the average, and about 95% is within 2, and about almost all of it is within 3 and -3. So outliers would be, like if you have extreme data points, if you're like more than 3 standard deviations above average in height, or something, or in something like that, or you're an outlier. You're very tall, or an IQ, or anything like that. Okay, now, what are we going to do? Now, many histograms are close to normal. So for these histograms, you can use the normal curve to estimate percentages for the data. It's just all you need to do is to know the average and the standard deviation of your data. And then you can do it. For example, let's say our heights. I think the heights are pretty close to normal. We can look at the histograms. So then if I knew that the average and the standard deviation of people's heights, I could figure out what percentage of the population fell in any interval. What percentage of the population is over 6 feet or under. So just by using a normal approximation. So what do you need to do? You need to, okay, but first you have to scale the data values to those of the normal curve. In other words, you have to make the average 0. So if the average was 65 inches, I'd have to make it 0. So I'd have to subtract 65 inches from everybody's to make it so the average person became 0. And then whatever standard deviation it was, like let's say it was 3 inches, I'd have to divide everybody by 3 inches so that so the standard deviation becomes 1. So that's standardizing. So you subtract the average and divide by the standard deviation, and that changes whatever value you have to z-scores. You can do this with non-normal data. You can do z-scores with anything, but you can't use the normal curve to find areas unless your data is approximately normal. So here's an example here. So let's just say, so what does this do? Subtract the average. You want to change, that changes the average of your values to 0. That's why you do that. Then you divide by the standard deviation, and that changes from whatever the standard deviation to 1. Okay, so that's what you do. Now we can see it here. So this histogram right here, so here's this jagged thing that's a histogram, right? And the histogram below approximates the heights for about 7,000 women, age 18 to 74, and looks like the normal curve, right? Like if you superimpose a normal curve above it, you see it's a good approximation. I mean, it's a little underestimate there, but it's a little bit of an overestimate there, and it's a smoothed out version of that, okay? But the normal curve has a mean of 0 and a standard deviation of 1. Well, this actual data has a mean of, for women here, their average height was 5'3½", and their average, and the standard deviation was 2.5. So you have to line it up here. So you'd have to subtract 63.5 from all these numbers. If you did that, then 63.5 becomes 0. And then you have to divide, so this would become what? 63 point, that's 2.5, 2.5 more than that. And then if you divide everything by 2.5, this distance of 2.5 becomes a distance of 1. So here's how all the heights line up. All right, so then once we do that, then we can use the percentages. We're going to be using a table, this table, to find percentages on the normal curve, percentage of areas. If you're in a different class, you would just integrate under this curve. Use the equation for this curve and integrate. I mean, if you were in a calculus class, calculus-based stats class. All right, so now what percentage of women are between 61 and 60 inches tall? So what do we have to do? We have to convert those to z-scores. So let's start. So we'll say z is what? Our value, just what we set up here, minus our average over our SD. And we want to convert 66. So it's 66 inches minus 63.5 inches, because that's the average. Where am I getting that from? That's right here. That's the, see, that's our average and standard deviation. Okay, so that tells me 66, that's 2.5 inches. Okay, so I'm 2.5 inches. It changes the average. It would change it changes the average to 0, and now I'm 2.5 inches, but I want to know how many, I want to change that to standard units. So how many, so I have to divide by the standard deviation, and that changes it. See, it gets rid of the inches, and we're in standard units. They have no units. It's a standard measuring stick. And what it means is a way we can compare data sets that are measured in different units. We standardize them. Now there's no units here. This means what? This means one standard deviation above the average. That's what it means. So if you see that, if you're one standard deviation, you can compare then something like, well, maybe this person is one standard deviation above average in height. What are they in weight? So you would change their weight to a z-score, and that's a way you can compare things that are different units. It's a common measuring stick. So now what is that, as long as weight was also normally distributed? What is a height of 61 inches in standard use? You'll do the same thing. 61 inches minus 63.5 inches over 2.5. And here we have this person, it's negative 2.5 over 2.5. So that's negative 1. So what does that mean? It means that the person is one standard deviation below average. So 61 inches is 1 SD below average because it's negative. And you can see how they match up here. See? Any questions on that? All right, so if a woman's height has a z-score of 1.2, how tall she is. What does that 1.2 tell you? It tells you that the person is 1.2 what? Inches? No, 1.2 standard deviations times the standard deviation above the average. That's what it tells you. How many standard deviations? So that's 1.2 times the standard deviation. So that's 1.2 times 2.5 inches added to the average, which is 63.5 inches. So that right here is 3 inches, added to 63.5 is 66.5 inches. So you can see, does that look about right? 1.2 is about there, yeah. It's 1 plus a fifth more. Okay, so now, so how do you find these areas? on the, so we're on page 28 here. So finding the areas under the normal curve. So we use this lots of times. You might be used to different charts. Sometimes they'll show you, charts will show you all the area below a z-score, above. I like to use, because this makes use of the symmetry of the normal curve, I like to use this chart that shows the middle area. Okay? And it's really useful to think of it this way when we come to confidence intervals. All right, so the area, I just told you that 1, 2, 3 rule. Here's the 1, 2, and there's the 3 rule. And you can see exactly. I said the area between -1 and 1 is 68%, but if we look on the chart, so this is our z-score. There's 1. We're going to look right there. And it's 68, actually 0.27. Between 1, there's no negative numbers on here because this gives you the area between -1 and 1. All right, and I said between -2 and 2 is 95%, but if you want to be more exact, what is it? 95.45. But we're going to just be doing a lot of rounding in class. Well, during lecture, and then at home, because I don't want to have to be pulling out my calculator all the time. And so the area between -0.75 and 0.75, so we'll just look, what is that? 54, about 55, but it's 54.67%. And between 3 and -3, we said was 99.7. Let's see what it says here. 99.73. All right. Any questions on that? So we're going to be using that chart all the time. This is our 1, 2, 3 rule. This is approximately 68, approximately 95. That's how you think about it. And this is approximately 99.7. And we can't just say approximately 99 because look how many of them are 99. Start with 99. Because the areas, as you get out, it goes on forever and it gets tinier and tinier and tinier. The tails do. Okay, so now we're going to put it all together. And we'll just do a few examples so you can do your homework, start your homework at least. And so let's see. When histograms don't follow the normal curve, don't use the normal approximation. But it's really easy. All you need to know is the average and the standard deviation. It's so useful you can figure out any percentages. So for example, so here's an average and a standard deviation. So what percent of the people weigh less than 120? Okay, well, the normal curve looks like this. So our first step is what? Our first step is we have to change our value to a z-score. So we have to convert 120 pounds to standard units by subtracting the average. So we'll say z is equal to, you take your value minus the average, and divide it by the standard deviation. So we get -30 over 20, which is -1.5. All right, now the second step will just be, we'll mark that z-score on the, right here, -1.5. So we'll mark the z-score on the curve. And let's shade this area that we want so we know what we want. Why am I shading this? Because it's less. So it's to the left. Mark z-score on curve and shade area that you want. You want to find. If it was more, I'd want that area. So now what do I have to do? Then I have to, my third step is use the normal curve table to calculate the area. So we have to use our normal table. So let's go back to the normal table, and what it's going to give us is the area between, there's no -1.5, there's just a positive 1.5 here, 86.64, okay? So that's 86.64, and Sometimes I'll say you can, that's approximately 87, that you can round the middle area. Why don't we do that so we can do these in our head better? So that's what's in the middle, to 1.5. So that's 1.5. So if that's approximately 87, what are these two together? The whole thing's 100, so these two together have to be what? 13 to add up. So this area right here is going to be, so the area is going to be 100 minus 87, that's 13. That'll give us both tails, but we just want one of them. So that'll be 6.5% approximately. So on your homework, I think sometimes it says you can do that, sometimes it says you can't. Just be a little careful. It will never, I don't think it will mark. Just follow the directions for the rounding. Okay, so that's your area. Now, what percentage of the people weigh between 120 and 160? So we'll just do this last problem. So we already know 120 is what? Negative 1.5. So now we just need the z for that one. So the z for that one is what? 160 minus 150 over 20. So that's 0.5. All right, so we're just going to mark it on the curve. So this is 0, 1, 2, 3. It's negative 1, negative 2, and negative 3. We already know the 120 is right here at negative 1.5. That's 120 pounds. And then our 160, this is the average, is 150. This is 0.5. We just got that. So that's 0.5. That was where our 160 is. And the middle is what? 120. Whoops, the middle is 150, excuse me. Oh. All right, so let's just quickly do this. That's okay, you can take a seat. All right, so just quickly do this. So what do we want? Right here, we already got this area was 87, right? So from here to here, all this will be 87 divided by 2, halfway, half of it. And now let's get this area, and this will be what? Right here, the middle area between 0.5 and negative 0.5, we look here, is 38 approximately. So that will be 38 divided by 2. Does that make sense to everybody? All right, so because we're just dividing it right down the middle here. So we got two pieces, so we have 87 over 2 plus 38 over 2, which is what? You want to do that for me? What is it, about 62 and a half or something? Is that right? What's this? This is 19, and that's, isn't it about, is it 62 and a half? Okay, so that's 6, it looks like it to me, 62.5%. All right, so that's where we're going to end because we've got to go.